Okay, here we are. Welcome to lecture 25 of Information Theory 2, Winter Quarter 2014, 21st century. What are we doing today? Well, according to this roadmap, which is something that I always listen to, we are here. So that means we're going to be talking primarily about strategies for computing the rate distortion function, and along the way we're going to see how those strategies can also be used for computing the channel capacity function. And in fact, they're almost identical strategies, as we will see. We're going to do a little bit more though today. First of all, let me remind everybody where we are in the reading. I always like to do this, because hopefully people continue to do the reading that way. Today we're going to start talking about these references, the Blehart and Aromoto papers, and we're going to begin to talk about, I don't think we're going to get to that today, but we'll begin to talk about the Scissor and Tusnedi paper. And now my inability to pronounce those names is immortalized on YouTube for the rest of eternity, and so therefore they'll know that I really am bad at names. Yes. So, okay, so right now we don't have any outstanding homework. What I want to do is get the grading, swap grading assignments done hopefully by today or tomorrow. So you'll get, just for those of you who are interested, what I think we're going to try to do is that everybody's going to have to grade 2 homeworks. So I'm going to do a random shuffle, or 2 random shuffles, and everyone's going to have to grade 2, and then I'm going to take some sort of aggregate grade for your grade of the 2 people who graded your homeworks redundantly. Should I take the min or the max?
You take the max plus 10.
The max plus 10? No, how about the max plus 1,000?
Yeah.
Right. That would work. Everybody gets a perfect score. That would work. No collusion, remember. Collusion is not allowed. If I detect collusion, that will be considered a serious offense, punishable. No, I'm not going to say that. I can't say that on YouTube. I would have said something now. If I wasn't being recorded, I would have said something very funny, but now you will have to sort of wonder what I was going to say. Office hours on Monday. So actually, this is another one of those weeks that I unfortunately can't make office hours on Monday because of a carpool situation, because my wife, who normally does carpools on Monday, is gone for 10 days, and so therefore there isn't going to be office hours on this Monday. But like I always do, you can create your own office hours by contacting me and expressing a desire to have a Google Hangout with me. I mean, President Obama does Google Hangouts now, doesn't he? So, I mean, there's no excuse for me not to do it. Since we're in such similar situations, he just gave the State of the Union address. I'm giving lecture 25 of Information Theory 2 at the University of Washington. We're comparable in that way. So, anyway, that's well known. Okay, so here's the question you've been wondering about on final presentations. So I want to spend a couple of slides talking about final presentations. So as you recall, there's not a lot of homework in this class, but a big part of the grade, in fact, a dominant part of the grade is basically your final presentation. So here's the first slide on what you're sort of expected to do. First of all, you're supposed to. I will talk about dates in a minute. Okay, so you will be giving a 10 to 15 minute presentation that summarizes 2 to 3 related and significant papers that come from transactions on information theory, Achievability. This is sort of the main journal. And in the past, people have chosen papers out of this journal, but I think since this is an information theory class, you should try to have at least 1 or 2 maybe papers from this journal. Okay, it's not absolutely necessary, and I've made exceptions in the past because the papers are very related, but on the other hand, you should at least begin your search, because part of the task is to do a significant literature search to find papers that you may be interested in. And they have to be significant, meaning that they can't be like non-trivial papers, although they can't be trivial papers, although, of course, there are no trivial papers in transactions on information theory, right? Now, the papers must not be the ones that we're covering in class. Now, you might say, well, how do we know? We're not time travelers. We don't know what's in your mind. We can't know what's to come and what are we destined to cover. So the way we do that is by you proposing a paper, and I say, it's not maybe as efficient as it could be, but it's reasonably efficient. It's you propose a paper, and then you say, you send it to me via the channel that I'm going to mention in a minute, and I say, sorry, we're going to cover this, can you choose a different paper? And that's not a problem. So one of the reasons why we want to start early on this process is because we want to give us the opportunity to iterate a couple of times. And to be honest, actually, it's pretty rare that I've needed to do that. So I think, in all likelihood, the papers that you propose, if you do a nice literature search, then we will not need to change it. So you need to do the research to find the papers yourself. So part of the assignment, like I could say, here's some nice papers, right? And I would find nice papers that obviously I wouldn't say you can't do. But I really want everybody to sort of get a feel of doing a broad literature search, which means that you might be needing to read 200 abstracts or 300 abstracts before you find a paper that you want. I mean, really think about spending some time on this. Okay? I mean, it's all online. The University of Washington gets complete free access to the entire history of the transactions and information theory, not just the last 10 years, and so therefore you should be able to, on the web, at your leisure, well, not too much of your leisure, but over the next week, you should be able to find papers that you like, or the next few weeks. We'll see the dates in a minute. The majority of the papers must have been published in the last 10 years. So basically you want to be somewhat present, because the goal of this class, one of the goals of this class is that once you finish it, if you get a reasonable grade, you should be able to read any paper in transactions and information theory. You should be sort of up to the present line of research. So that doesn't mean that you know everything, but it means that you should be prepared to learn anything. That's sort of, in some sense, the whole goal of graduate school. It's like you're not here to graduate being omniscient. You're here instead to sort of be able to learn anything for your future careers. Your grade is going to be based on how clear. I mean, this is a presentation, so I'm going to grade, in some sense on the content of the presentation, but also on clarity and how easy it is to understand your presentation and how accurate your presentation is. And accuracy is going to be hard to judge. It means that I need to sort of read all of these papers that you guys are proposing. Some of them, of course, in fact, many of them probably are ones that I haven't read. So this will also be a learning experience for me. But basically, the grade is going to be, you're going to be up here. I think we're in this room, but you're going to be giving a presentation. Should I put them on YouTube? I could do that. You could broadcast them on YouTube. That would give you a little bit of pressure. That would put some pressure on. We'll talk about that. But anyway, clarity is really clear. And clarity is not only going to be based on what I understand about your presentation, it's going to be vicarious clarity, meaning I'm going to assess the clarity based on how I think other students in the class are finding the presentation. So in other words, I'm not only going to be looking at you, I'm going to be looking at other people's faces, and if I see lots of smiles and nodding heads, that basically means that it's an indication that you all have understood the presentation. Now again, no collusion. I don't want to hear about you planning, okay, when I give the presentation, everybody nod right at this point. This is the most critical, confusing point, and if you all nod, he's going to think that you understood me. So don't do that. You really want to be understood, so no collusion. So I want everyone to expect this to be a challenge. It's not just, a week before the deadline. I mean, like I said, there's no homework in this class, but on the other hand, this is an advanced graduate class. I want this still to be considered a significant research challenge. And because you're advanced graduate students, you should be self-motivated to do a lot of work on this. I will offer you the opportunity to make these milestones, as I will talk about in a minute. But it's a real challenge, so it's going to require real work and real time. It's not as tangible as, like, for example, a hardware project where, week number 4, you have to get the LEDs blinking in a particular way. We don't have those kinds of tangible measures of progress. We only have my weak assessment of what you've done via these milestones, which I'm about to describe to you. Right, so this last point is to, if you want to get a good grade, you will need to work very hard to present a very complex set of ideas in an extremely simple and precise way. Now, so what does that mean? This means that you will need to think hard on two fronts. One, to just understand the papers to begin with, because that will itself be a challenge. But there's going to be a secondary challenge, which is really a challenge that teachers face all the time and researchers face all the time. And I think in life, in professional life, one should consider this a challenge all the time, which is how best to take a very complicated set of ideas and then via real empathy to your audience, convey those ideas in a clear way that everybody will understand. Think about different strategies. Well, I could do it this way, I could do it this way, I could do it this way. Is going through this proof necessary to understand that proof, or can I convey this proof without really understanding that proof? Or have I defined a term? Have I properly expressed a term, or before going on to something else which uses that term? How much time do I spend defining each concept before I move on to the next concept? Those are the kinds of things that you'll need to optimize over. The order that you present the material, especially when you have multiple papers. If it's multiple papers, that means that the papers don't have complete overlap, and so you'll still have to present in a very short amount of time these ideas. And obviously you can't present everything. You can't just read the papers. But what I'm hoping you can do is really convey those papers. Now, you might, since you know your goal, since you know this goal here, you might then choose these papers that are, on one hand, interesting and complicated, but for which it's more viable to do this bottom goal. Like, it might be the case that there are some papers, and no matter what, it's impossible to present them in 10 minutes reasonably. But on the other hand, think of this as a challenge. I mean, you are all graduate students. You're going to be publishing papers in conference. You're going to be going to a conference. You're going to be having conferences where there are times that you have 10, 12, 15 minutes to present the papers. Sometimes these will be complex ideas. In fact, often they'll be complex ideas. In these conferences, you will be the world expert on that material because you're the one who knows what happened more than anybody else did. And so your goal when you present a paper at a conference is to convey that idea, is to make it such that the people in the audience feel happy that they understood everything that you said. So that's essentially what you're practicing. So this is then a meta goal on also on something that you'll be graded. Everybody got it? Okay. So milestones. Yes. Also, last point. So we might need to try a few topics. I think I kind of sort of said this, but you might need to try a few topics until you find the one that's most suitable. I'm just lowering the screen a little bit. Of course, the YouTube audience doesn't need the screen lowered. Okay, so what are some milestones? So, so all submissions are going to be done, like always, in PDF format through our Dropbox. So we have a bunch of deadlines. So on Monday, February 17th, which is about, I don't know, that's like 2.5 weeks from now, I think. Is that right? So Monday, February 17th, you need to have candidate proposed papers submitted and include, at most, and I really want to emphasize this at most, because sometimes what people do is they'll like send me 10 pages of paper proposal, including like entire pages of quotes from the paper. I'm like, no, that's not the assignment. That means you've not succeeded in understanding what this assignment is all about by sending me more than one page. Okay, so part of the assignment is, again, to be able to express complicated ideas simply. And so by forcing you to have one page, raise your hand if you understand by this, if you acknowledge one page. You wouldn't believe how many times I've said one page in the past. I've been saying this for like 10 years now. And there's never been a class that I've taught where I've asked for one page, where everybody sends me only one page. Let this class be a first. Okay. So one page, did I mention one page? One page write-up. And then what you should have in that one page write-up is, number one, why you chose these papers. And I'd like to see these bulletized answers. how they are related to each other, why they are important for pure information theory, and 4, how they are fundamental and deep. What does deep mean? It means many layered.
Pure information theory.
Well, I would say that it's something that would be considered. I mean, one way you could say this is that it's something that sort of fundamentally advances the understanding of channel capacity in like network information theory. You know, something that's sort of a core goal of information theory, as opposed to, say, for example, here's a paper based on neurobiology, or that's in the neuroscience community, and it talks about neural coding, and it uses entropy to describe some aspects of the neural code. And that's using entropy as a tool. I don't think that's really sort of a fundamental advancement in information theory. I mean, your goal in this class is sort of to be able to read and learn about any paper that might occur at Transactions in Information Theory 2014. Right? And so if it's a paper about using entropy as it was understood in 1948 for understanding the neural code, that's not really a core IT paper, irrespective of how important it is for neurobiology.
If it's in the IEEE transactions, that's a pretty good indicator.
That's a good indicator, yeah. And I think that, I mean, I hope that you just don't say, well, obviously it's important because it was accepted by transaction in information theory. I hope you offer a little bit more evidence than that by, you know, indicating that you've understood the paper and this is what it does and this is how it affects it, or this is the potential that it might have. It might actually lead to this great discovery and all this kind of other stuff. But on the other hand, indeed, if all your papers are from transactions in IT, you'll have less to do in that point than you will if all your papers are from transactions on horticultural engineering or something. Whatever that is. And then lastly, how you'll summarize these papers in a simple and a precise way. So all these 5 points need to be addressed. Now, then every week from thenceforth, you'll have a deadline on Monday at the same time. So every Monday at 11:45 p.m., you'll have such a deadline. So the next deadline will be the next Monday. And the idea is that this paper, for the first deadline, you'll sort of have a bunch of papers, and I might say, oh, actually, maybe you could try some other papers. And then, so this first deadline is absolutely non-binding, so you're not obliged to stick with those. But hopefully by that point, I mean, you have 2.5 weeks to search, and I would start searching now. I mean, like I said, you might read 200 abstracts. Start reading abstracts, yeah?
So all the 3 papers can be like about the same topic, right?
Yeah.
So that they don't need to be like different topics and sort of related. Can be purely about the same topic, but
I mean,
different aspects of the same.
To answer that question, think about how one would present 3 papers that are entirely unrelated in that 15-minute time limit. Right? Think about entropy compression. If they're independent papers, it's going to be harder to compress 3 independent sources than 3 dependent sources. So think about, again, the papers from the perspective, on the one hand, they need to be significant, but on the other hand, they need to be clearly summarized in a short amount of time. Like one of the papers might be sort of like the necessary background or something, or sort of some of the mathematical background. I mean, one of the papers might draw even from mathematics that comes outside of the IT community, just to sort of get used to the notation. Try to use simple notation. You don't have to use the notation that's in the paper if you develop your own and better notation. Oftentimes, the first time an idea is presented, in fact, it's almost never that the first time an idea is presented is that the clearest way. The best books, if you go back and look at Gauss's paper on Gaussian elimination, it's not very, even not even considering that it was in Latin or German or something, it wasn't as clear as the way you look at Horn's book on matrix algebra and you find this fantastically, beautifully written chapter or section on Gaussian elimination or something. So lots of ideas are presented much better once they've been digested, and so this is also an opportunity for you to digest these ideas and represent them in a clearer way than they were originally presented. So then you next have a deadline on March 3rd. I mean, the emphasis on this one was to try to have a little bit more discussion on sort of coherency and simplification of the presentation. You might say, oh, I've decided to use this notation this way or something, because it's much easier. And it gets rid of all these extra indices which aren't core to the main idea of the paper. So there's an updated write-up. I mean, this is like a progress report, what you've done past week. And then finally, we're going to have final presentations on Monday, March 17th, from 2:30 to 4:30 in Low. Is this 102? I think we're in 102 now. So it's going to be in this room. And then what to turn in is that there'll be your presentation, and then you'll have a 4-page summary of the papers at the end. So that has to be strictly 4 pages. So what I'm going to do is, I haven't done this yet, but on Canvas I'll make assignments for all of these things, and that will be where you. So I think you get email when I create assignments, or you get some sort of notification. So you'll see them. And again, PDF. I don't care what form. You could do it on hand. You could do it by hand and take a picture, and that's also fine as long as it's readable. You could use LaTeX or any other system you want, but PDF is what you have to submit. Okay, any questions on the final assignments? Okay. Okay, let's do a review now. We've been talking about rate distortion, and we had, this is this key theorem. I think this is from 2 lectures ago now. We have the rate distortion function, which is the infimum of achievable rates at a given distortion, which is this. And then we have the information rate distortion function, which is the result of this optimization problem. And the theorem that we proved was that these are identical to each other, which again really means that achievability means that the achievability of a pair means that the rate is lower bounded by the information rate distortion function. And then secondly, that if you have a pair such that the rate is lower bounded by the information rate distortion function, then you can find, or then there exists some code. There exists a code, a sequence of codes. So here's the achievability idea. I've already just said that, so I'm not going to say this again. We defined the notion of distortion epsilon typicality, and it was very similar to the joint typicality that we saw in the channel capacity case, except that we added this last condition on distortion typicality as well. And then we have these distortion typical sequences, and we saw that the distortion typical sequences eventually get all the probability. Same sense. We have these 2 additional subsidiary theorems, which, on advice from you guys, I've changed the names to lemmas. What a brilliant idea. Mathematicians are very smart, that they entropy code commonly used concepts like subsidiary theorem. I think what had happened originally with those slides is I was doing those slides after when I was in a drunken stupor and I had forgotten that the word lemma exists or something like that. So in any event, this theorem is one that we used, and we don't need to say it again because we already talked about it. This theorem, which might in fact be useful in other contexts, but I thought it was interesting enough to go through the proof. And we use those theorems just to remind folks. And then we also had this geometric view of rate distortion. Remember, and we talked about that at the end, which was sort of an intuitive notion of the dual nature between rate distortion and channel capacity, whereby in channel capacity you're trying to pack as many small balls into large balls, or pack as many small spheres into a large sphere without having there being any overlap. And in rate distortion, what you're trying to do is make sure that you cover. You're trying to put as few small spheres into a large sphere while ensuring that there's no point that goes uncovered. So on one hand, you're trying to pack as many and minimize overlap, or have no overlap, because that's going to mean that there's going to be error if the small spheres lie on top of each other. And then in the rate distortion case, you're trying to put as few small spheres in there while making sure that there's no point that's uncovered, because if there's a point that's uncovered, then that's a point whose distortion is going to be greater than the exemplar that lives within inside of the small sphere that's closest to that uncovered point. And so we talked about that here. And then the minimum of such code words that we get is very similar to the channel capacity. It's the ratio of these entropies. This is the Gaussian case. But basically we just get this quantity, which is really that was the form of in the Gaussian case, the rate distortion function. It's log of that thing is divided by n is 1/2 log of sigma squared over d. That's the rate distortion function. Here it is down there, in fact. Okay, so today, what we're going to do is several things. First of all, I'm just going to very briefly have one slide on the general multivariate normal rate distortion. I'm not even going to go through it because I think because we've already done the Gaussian channel case and it's analogous. And we're going to talk about, after that, we're going to talk about computing the rate distortion function and the alternating minimization procedures. Which, for those of you who are interested in, say, for example, like machine learning, I think would be interested in alternating minimization because it's a general convex optimization technique that's very, very simple to code. Oftentimes it works really, really well and it's very, very fast. And it's also the way that the EM algorithm works and a number of other algorithms. But let's first of all talk about multivariate normal. So in the multivariate normal case, unlike before, we actually have a correlated sources, X, with Gaussian, it's a multivariate Gaussian with covariance matrix C. It's a general positive definite matrix. So the question is, what do we do there? But very similar to what we did in the channel capacity case, we sort of decorrelate by doing spectral factorization of the covariance matrix and sort of rotate the matrix into its orthogonal directions, and where the variances essentially become the eigenvectors, the eigenvalues of that covariance matrix. And then if there's like a joint distortion constraint, which we saw, we would run then the reverse water filling argument on the eigenvalues of C. So remember, in the channel capacity, we did the water filling discussion. In the rate distortion, we did the inverse or the reverse water filling process. But in here, we do it on the eigenanalysis. So the eigenanalysis aspect of this case is exactly analogous to the eigenanalysis aspect of the channel capacity case when you had correlated sources. So I've already said that. And I guess that's all we need to say. And I'm thinking about possibly adding this as a problem set of going through the analysis or just writing it up for yourself in your own words, because I think it's not so uncommon, but it would help to solidify your understanding of the channel capacity case and at the same time allow you to see another example of this in the rate distortion case, because we need to have a good problem on rate distortion. So this might be outlining this process of problem set. So don't be surprised. Okay, so next what we want to do is we want to talk about computing the rate distortion function, because like I said last time, I mean, in these special cases where we have, we know everything about the model, we know it's a Bernoulli distribution, and we know a particular, type of very easily analytically expressed distortion function that we've got, we can compute this information rate distortion function exactly and analytically, like for example 1/2 log of sigma squared over d for the Gaussian case, right? But that's actually fairly rare. And in general, we don't have any such property. Maybe we only have some sort of numeric expression or numeric specification of the distribution of x and its properties. Like maybe we know that it's drawn from some p, but we don't have really a good understanding of p. Other than we can compute it, but it's not a Gaussian, it's not a parametric distribution. Okay. So we still, however, want to compute this, right? We still have a distortion function over x and its sort of vector quantized cohort, x hat. And we still want to optimize over conditional distributions, which again, we might, you might think of this as a conditional probability table over discrete sources, in which case all you have to optimize over is this big table, and you can't just express them. And we need a way of essentially optimizing this thing. So let's then look at this from this problem, 25.1, as a more general optimization problem. So what we've got is the following. We're going to restate the rate distortion function in the following. Let's zoom in a little bit on it so we can see it. So it's a function of the distortion, but it's this optimization problem. So we want to minimize the mutual information. So the mutual information is the underlying objective. And we want to minimize it over conditional distribution. So remember, p of x is fixed, and so we're optimizing it over the conditional distribution. But we have a bunch of constraints. right? So it's not so we can't just say minimizing it over the conditional distribution. We need to express what it is about a conditional distribution that makes it a conditional distribution. And so let's say we minimize it over this matrix. So this then becomes, this is really just a matrix. We're minimizing it over this matrix of values, subject to, on the one hand, it has to be non-negative. 2, it has to be normalized. And I guess if x is considered the rows and x hat ranges over the columns, it's saying that each row has to be normalized. Right? So it's row normalized to 1. Thirdly, we're going to add this constraint, which basically says that the expected distortion according to the what's now a distribution Q is equal to D. And I'm going to talk about why we say equal, because in the previous case we said it's less than or equal to D. Right. I don't know why it's not looking that good, but let's use a different color. Maybe let's use green again. Okay. And then lastly, we have this definition of the mutual information, which of course is just this. And this is the mutual information according to the current distribution that we're optimizing it. And also we have this expression for the marginal on x hat using the conditional distribution. So remember, P of x is fixed. We don't get to choose this guy. What we're optimizing is over this guy. But for any particular choice of this guy, we've got this as the marginal over x hat. So that's just sort of automatically given. Okay, so does everybody see how this is the rate distortion optimization problem? And what we're going to do, first of all, is we're going to see eventually that this step here is going to be seen as a form of projection, interestingly enough. And we're not going to see this probably until the end of today's lecture, but doing this marginalization can be seen as a form of an optimization problem via a minimization process, which can also be seen as a projection. But first of all, what do we mean by a projection? So a projection is like the following. We've got some, maybe I shouldn't call this a distance measure. In fact, I think I would probably be incorrect mathematically to call this a distance measure. So we've got some, let's just say it's a distortion measure or divergence measure. Like, we're not insisting upon it, say, for example, being a proper distance where it maybe satisfies the triangle inequality and it sort of corresponds to some Euclidean embeddable distance of some sort. So let's just weaken that a little bit. And then we have a constraint set, P, and a vector x hat that's not in P. Okay, so script P is just some set and x hat's not in P. And what we want to do is we want to find a member of P that's as close to x hat as possible, where closest is measured via this distortion measure. And so in other words, we want to find a member of this set. One thing, this is just as an aside, if you don't do this already, I wouldn't call it a pet peeve, but whenever you say argmin, you should use in rather than equals. Why? Because argmin is a set. Argmin is not a value. It might be a set of size 1, but officially, this is my pet peeve, officially argmin is a set, so if you say x is equal to argmin, you're saying that x is a set which contains 1 or more values, or possibly 0 values even. But if you really want to be accurate, you should always use in rather than equals. So anyway, to do this projection, we choose an x hat that's in the argmin set. Okay? And graphically, you can see it this way. So let's view our constraint set P as this plane. Right? So I have this fantastic figure which I spent time producing, and now I'm going to adulterate it by mucking it up with my annotations. But you can always zoom back, or I should say rewind, to the point of the figure where it was still unadulterated. But in any event, you've got this plane P, and you've got this vector here. Okay, so the vector is outside of the set, right? That's x hat. And then you want to try to find the one that minimizes it that's in the set. And so if everything was nice and Euclidean, what you would find is that the solution, which is this vector here, which lies within P, is orthogonal to the error, right? X hat minus x. So that's a very common result. But you can sort of imagine that's what we mean by a projection, according to some distance. Okay. Now, in the original, getting back to the original optimization problem, this is just getting back to this optimization problem. We have both equality constraints, namely these guys, and inequality constraints. Right? The inequality constraints ensure that the probability distribution, probability values are non-negative, because if they're negative, it doesn't make any sense. But and the equality constraints ensures that everything sums to 1. If it were the case that we relaxed and we eliminated this set of constraints entirely, and we were lucky and we got a solution where everything was non-negative, what would that mean? It would mean that those constraints are never active, and they weren't necessary. They wouldn't have changed the solution. Right? Because if this minimum is the same, if the minimum without this constraint, 25.3, results in a conditional probability distribution which is non-negative, it's still going to be a probability distribution because this other constraint, the equality constraint, still sums to 1. Right? And it means that adding that additional constraint, which further, when you add constraints to a minimization problem, the only thing that can happen is that the result of the minimization can get larger, right? Because you're restricting the set of things that you're optimizing over. But if you relax the constraint, if you get rid of this constraint, and you get a solution which satisfies the constraint, then you know that adding that constraint didn't do anything. Right? This is everything in everything, as you will see, is convex. Right? This is something that relies on that. But basically, we've got a convex objective in this matrix. P is fixed. We've got a convex objective in that matrix. Okay. Now, one thing to recall is why. So in the thing we said that the one is an equality constraint. We did have a different. Remember in this version we said that this was less than or equal to D, right? In this form of the optimization problem. But here we're saying that it's equal to D. So why is that okay? Why is it okay to say equal to D? Well, remember there's that theorem that we proved, which basically says that when D gets bigger, R of D can only get smaller. So R of D is monotonically non-increasing with increasing D. So therefore, if we just set D to its maximum value, there's no chance that we'll have ever further restricted D. Right. So we can always get the solution where it's right exactly equal to D. That's again also based on the property of, it's right closed and upright closed, the right distortion function. So therefore, we can simplify by getting rid of this inequality constraint and just turning that one constraint into an equal constraint. And then the second thing was the thing that I was talking about a minute ago, which I probably should have waited until after this. But first of all, is everybody happy with this point? Again, it's based on the properties of the rate distortion function itself, which we know, we've already analyzed. Remember, the function looks like this. We know it's convex. We know it's monotone, non-increasing. Now let's also do this thing I was talking about before, where we relax that remaining inequality constraint, which is the non-negativity constraint for the entries of the matrix. And if we were to relax that constraint, we would get the following Lagrangian form. Okay, so we've got a Lagrangian because we've got this first part here. You know, I really need to start bringing water to these lectures. Some people drink water like every 10 minutes. I probably should do that. But actually, does anyone know, is there a water machine in this room? Sorry, in this building? There's one down the hall. Okay, so I will use it. So the first term, which is currently highlighted in yellow, is the mutual information. The second term, which will be highlighted in green, is the is what? That's the now equality constraint. And the third term is basically the sum to one equality constraint. And we have one Lagrange multiplier associated with equality constraint, and then we have a whole bunch of Lagrange multipliers associated with each row of the matrix, ensuring that it sums to 1. Okay. I hope it's the row. Okay, so again, so this objective is easily shown to satisfy Slater's condition, which means that strong duality holds. And moreover, all the constraints are nice, friendly, affable, differentiable objectives. Affable is the English literature equivalent to differentiable in mathematics. Question?
Does it satisfy Slater's conditions because Zero lacks that one constraint?
It would satisfy Slater's conditions even with, but what we're going to do is, in order to sort of get an intuitive reason for why and how best we can solve this objective in general, and then which leads us to alternating minimization, we want to relax it at first. So it still will still have strong duality, even with the inequality constraint. Remember, Slater's condition is the thing that says that there has to exist a feasible point in the strict interior. Feasible point. That's always clearly going to be true. It just means that there has to be something there has to be a probability distribution, right, that has that distortion. So let's going back to this bit here. I should probably do this method. Oh, forget it. I don't know where it is, where that slide is. Let's just go forward. Okay, so the KKT necessary conditions for optimality hold. And so we can then, thanks to the differentiability of everything, we can take the objective and differentiate it with respect to the entries of the matrix that we want. And for doing that for each x and x hat, we get this many equations, right? That must equal to 0. And then we've got the equality constraints. In terms of the Lagrange multipliers, we've got these additional Lagrange multipliers. How many equations and how many unknowns we have. We have the unknowns associated with the matrix, which is q of x hat given x. We have the unknown associated with lambda, the Lagrange multiplier associated with the distortion equal constraint. And we've got the Lagrange multipliers associated with each row of the matrix. So basically we need x times x hat plus x plus 1 equations, and which we get by these sorts of things, by these things. So we have the same number of equations and unknowns. So this should say plus x plus 1. So now here's getting back to this other thing I was talking about. So if it's the case that once we've done this, removal of the equality constraints, if it's the case that this conditional distribution is greater than 0, then we've solved the problem since without actually needing those constraints, and so therefore those constraints aren't active. Right? In fact, I'm just thinking, I hope I'm not wrong in this, but I don't think we actually need this to be strictly greater than. I think it can be less than or equal to, because if it's less than or equal to, if a value is actually equal to 0, without actually asking it to be greater than or equal to 0, that constraint wasn't there either. So we can strengthen this a little bit by doing that. Now the question is, when might this occur? Now this is really important for the intuition, this next slide. It will make sense. So when might it occur? So what is it? What is it, first of all? So it is the following. So remember, we've got a distortion, and we're interested in the given rate, right? Now, what does it mean for one of those guys to be 0? So if for example, we do this optimization, and we find that, let's move to the next slide. We find that P of x hat given x is equal to 0 for some x and x hat. So if that probability is 0, it's saying, okay, for that x, I'm not even going to use that symbol ever. I'm not going to use that x hat ever. Okay. And moreover, it would strengthen. Suppose it's the case that for all x, this is true. We find that, without actually having this constraint. What would that mean? Would that mean that the distortion is high or distortion is low? Because turning off code words corresponds to increasing distortion. Exactly. If the distortion is very, very big, we can get by with a 0 rate code and map everything to one code word. Right? That's a 0 rate code, right? By just mapping it to the number 4, always, no matter what. So obviously we're not going to retain any of the information, but that's okay. We can still retain none of the information and achieve that particular distortion. But in general, as the distortion gets bigger and bigger, we can begin to turn off these code words, right? And turning off these code words should manifest itself in the optimization problem by zeros appearing in this conditional probability table. Right? So let's back this up with font description, with a textual description. So when we have a small distortion, that requires, and we know the shape of the rate distortion function. We've already analyzed the shape. When we have a small distortion, that's going to acquire a higher rate, meaning that we're going to need to use up our resources. We need to use up all of the symbols, all of the code words that we've got, because absolutely every code word is sacred in such case. None can be abandoned. Everybody counts. However, when the distortion, this is something else. So Dmax, remember, Dmax is the point at which the distortion, the rate goes to 0. It might in fact be, we might have rate distortion codes where that never happens, where the zeros never happen until we suddenly get to above the Dmax point, the critical point where the rate hits 0. But it might happen before. If there's one or more of these conditional probability guys that are negative, without the constraint, so that sort of means that maybe that those things should be turned off. And in fact, because everything is convex, what does this mean? It means that the true minimum of this mutual information value falls outside of the probability simplex. Right? I guess what I'm saying is that this expression, the expression for mutual information, there are cases where you can still evaluate that even with non-probabilities. In fact, there's Kullback, and if you look at his book, he's got a generalization of Kullback library divergence for non-probabilistic measures, and it's basically the same form with some fix-up stuff. But let's define the probability simplex as this, as triangle sub Q. So basically, triangle sub Q is the set of matrices that are such that the rows both sum to 1, and each entry is non-negative. So each row is a probability distribution. And so if we do this optimization without the greater than or equal to 0 constraint on each of the entries, it means that minimum falls outside. And so we can sort of visualize it. Let's just visualize it. So here we've got this objective here, which is, we know it's convex in the argument. We look at the true minimum, And let's say that this guy is the true minimum right here. The true minimum is right there at that x. But it might be the case that that true minimum, the objective, falls outside this green probability simplex. Meaning any point within that green triangle corresponds to a probability distribution, and any point outside has one or more entries which is either negative or greater than 1. And since everything is convex, thanks to the convexity of the simplex constraint, because the simplex constraint is a convex set, right? Probability simplex is convex. You can take two mixtures of distributions, convex mixture of probability distributions, you've still got a probability distribution. It's a well-known result. So in such case, I mean, this is a result from convex analysis, but when everything is convex and you've got convex constraints, if you violate one, what you do is you project it on to this set, the nearest point. Intuitively, this should make sense. It says, okay, well, this is not, maybe, this is where I need to start annotating this thing. Pointer would be great, but this point is not in the simplex, but here's the nearest point that's in the simplex, and so what I want to do is move it. I want to sort of look at this as a distance. As I want to choose it to the point in the simplex which minimizes that distance, according to some distance or distortion or divergence measure. And that will be the true solution, thanks to the convexity of the constraints and convexity of the sets. This doesn't work in non-convex optimization, obviously. So then restated, since this is convex and the objective is convex, the minimization with the constraint must lie on the boundary of this convex set. And this basically follows, and you can get this from the KKT conditions, strong duality, all this stuff. But we're not going to prove that here. Hopefully you've proved that in your convex analysis class. Have you guys covered this point yet in that class? You will. So now when you get to that, you will say, I know that. I learned that in information theory. What a nice pair of classes to be taking. That are, see, we're friends. We're friends with that class. That class and this class are best of friends. So this is really a general point in convex analysis. So when we do convex minimization of our convex set, an update to minimize the objective that, say, ignores a particular constraint, if you can then update that and project it back onto the convex constraint. And it has to be projected onto the nearest point. So it becomes a boundary point. And let's assume that everything is closed. So that makes sense. So let's go back to our particular problem. So if the solution, so now we're not going to prove this because we're not a convex analysis class, but on the other hand, I hope that the intuition is strong, that this is true. So I just want to give you the intuition because we want to use this result. So what this means for us here, in the context of computing rate distortion, if the solution to the problem without using that inequality constraint, which is the non-negativity of the entries of the matrix, if some of them, say, are negative, then we just project it back on. We project the solution back on to the convex set at the boundary. And what point lies at the boundary? It's going to set them to 0. Because if they're negative, then it's going to be 0. So in 2 dimensions, you might wonder what does this convex set look like. So here's, say, 0, 1, and here's 1, 0. And this is the convex set, right? So basically any point in here corresponds to a probability distribution. So if we get a bad point, like down here, we just sort of project it up to this point here, to a good point, where one of the entries is 0. Okay. Everybody like this? Everybody happy with this description? But what that means is, getting also back to our particular application from rate distortion, it means that now we've turned off that code word. That code, if we get a negative, it's going to turn it off. Now something even more remarkable is going to happen. And I don't know if the order... let me just follow the slides, because I'm getting a little bit ahead of the slides sometimes. But what this means, like I just said, is that we can then remove the alphabet symbol, or perhaps several such symbols, and we might hope to be able to remove several such symbols, or possibly even more hopefully, let's say that it happens for one particular value of x hat and for x. Now that means that for this particular x, so remember the difference between x and x hat, remember x is what we're sending and x hat is the code word. Let's say that for particular x, it decides the probability of x hat, a particular code word, is 0. But that doesn't really help us truly remove it from the alphabet, because there might be some other x, like x prime, where that x hat is not 0, which doesn't remove us. But what we're going to see is the remarkable fact that we will be able to do that. But before we do that, let's just make sure that we understand that this happens for big D, for distortion. And this should start happening as D gets bigger and bigger. Now, we're going to get this really nice property by solving this sort of, I guess it's not really correct to call it partially unconstrained problem. Yeah, it's correct to call it a partially unconstrained problem. But before we do that after the break. But before we take a break, let's make sure that I've given everybody an opportunity to ask questions. So are there any questions?
So you were just saying, so if q of x hat given x equals 0 for some x, then you're saying that we'll see that in fact we can just turn that code word off, even if there's other q of x hats given x's for other x's that are non-zero?
Yes, that's exactly right. Now we don't know that yet, but we would hope, at this point we might, based on this point in the analysis, say, boy, wouldn't that be a great thing if that happens to be the true case?
When we do that, do we have to redistribute that probability mass to the other x hats?
It's going to happen automatically for us, as you will see. I mean, it's remarkable. And this is why I think the whole notion of alternating minimization and when this thing happens is going to be really easy. And actually what you're going to see is computing the rate distortion function is unbelievably easy once we do this, thanks to this property. So we don't need to do this redistribution stuff like, oh, you're all out of balance, but it's another, but we'll answer that question. Okay, so I answered it partially, but you're going to see it's a lot easier than it sounds like it might be. Okay, so any other questions? Okay, let's start again. This is again the second half of the class after a Camtasia crash. So what we're doing is we're defining mu to be equal to this quantity. It's basically e to the negative nu of x over p of x. So remember, nu is our Lagrange multiplier. It's the Lagrange multiplier associated with each row of the matrix. And so then we can obviously express it in this form. So again, let's express the Lagrangian objective. And since we're going to take the derivative and set it to 0, let's not write any of those terms that get canceled once we take derivatives. And so we have the Lagrangian objective, and we have it in this form. So here's the mutual information guy here, and then here's the distortion. Here's the this one summed over this bit here corresponded to the distortion equality constraint, and then lastly this, along with this stuff here, corresponds to the sum to 1 constraint. And now since this is in this form, we have this expression of nu over p as the negative log u. We can actually bring that inside of the log to look inside of it. So what we've done is we've brought mu down here. Okay. And then we can write it just very simply as this form with beta, where beta takes this particular expression. Okay, so it's actually starting to look a little bit simple, but on the other hand, it's going to allow us to sort of solve this fairly easily. So when we take the derivative of the objective with respect to the matrix, the thing that we care about, and set it equal to 0, we get this. Okay, and a little bit of algebra, it's like a couple lines of algebra shows this. And once we do that, we get an expression, a really remarkable expression for Q. Now remember, this is the expression for Q in the case when we're not using this non-negativity constraint. Okay. So let's see if we should spend a little bit of time looking at it. First of all, let's look at it this way. This is something that's really important because, first of all, it says that the matrix for row x is basically proportional to q of x hat, where q of x hat is just the marginal over x hat. So everybody involves q of x hat, and then when it's weighted by this distance, or by the distortion measure. In fact, it's e to the negative lambda times the distortion. And then it's normalized by mu. Right, down there. And so we'll talk about this, and this is, again, I think I'm getting a little bit out of order of the slides, but this seems to be a reasonable time to talk about this. If it's the case that for given x, the distortion between x and x hat is big, what's going to happen to the conditional distribution? It's going to downweight that probability. It's going to say, well, I don't think that's probably a very, very good thing. On the other hand, and this is something we need to show, this sort of might get us to think that, oh, look, if one of these guys, if there's 1, 0 in q of x hat given x, so if one of these entries here is 0, well, that 0 is not going to happen because of this exponential, right? It might happen if mu becomes infinity. And it seems most promising that it would happen because of q of x hat. But if q of x hat is 0, then all of the x hats are going to turn off simultaneously. And if this doesn't make sense, I have other slides to show this. But first of all, let's see if we can come up with an expression for mu. And in fact, we can, because this has to be a valid probability distribution. And just thanks to the properties of the valid probability distribution, we can get an expression for mu, which is just the normalization constant. It's the thing that we need to do to normalize the numerator to make this thing over here a probability distribution. So what that means then is that mu, I think I have this. No, I don't have this. Saying that mu is equal to this. So what the bullet point says is that if we can solve for q of x hat, if we can solve for this thing, then then thanks to everything else, since the distortion is fixed, right? The distortion is just sitting there. That was just given to the problem. We can get this conditional distribution as long as we can get q of x hat. That's sufficient. But let's I think do this thing that I was talking about. So here's the update again. So there's the thing, and then I do have some slides on this. So the first thing to note is that to make it a valid normalization, we need to do this, right? And the reason for that is because of the fact that each row of the matrix needs to sum to 1.
I already forgot what mu was. It was like e to the...
Yeah, so mu, remember, we define mu of x to be equal to e to the nu x over p of x negated. I believe that's right. Let's just double check. Yep, there it is. So, first of all, does everyone see that right now we also have an expression for, we have this expression for nu as well. Secondly, and then this is the intuition we were talking about before, if it's the case that the distortion for a particular x hat is very, very big, then that's going to bring down the conditional probability. And that makes sense because it's saying, well, this is a really bad surrogate. The distortion, I've got a particular x and I want to find a code word for this, and here's x hat. That's really bad, right? It's got a huge distortion. Therefore, you shouldn't use that with high probability, and that's exactly what this says. Right? So that sounds good. But on the other hand, this is balanced by q hat, and it's saying that, well, if q hat is sort of marginally necessary, if q hat is something that's always needed because, for example, q hat, there's no q hat. If q of x hat is marginally necessary, what I mean by that is that if this is big, it sort of forces you to use it, right? Because it's saying, well, absolutely, for some reason, maybe because my distortion constraint is my distortion is very small, I still might use that if that marginal q of x hat is small. So when q of x hat is strictly greater than 0, and the reason for that is because we're going to need to divide by it. So when we can actually construct this, we can compute this quantity. So as follows. So where do we get this? So q hat, remember, is the marginal. So what we're doing is we're just plugging in. We're saying q hat, which is the same as this, is equal to the sum, which is the same as this sum, which is equal to this guy, which is the same as this guy, which is, and then we're just plugging in our expression for q of x hat given x, which is this guy. And now we can then rearrange things by pulling out the q of x hat, since that's not part of the sum. And then once we do that, we can cancel everything out. And we just get that this is equal to 1. So what we get is that this whole thing, this expression here, has to equal 1. There's nothing magical, just algebra. And here we go. So then now what we do is that for each x hat, the reason why q of x hat has to be greater than 0 is because these x's that we can't just divide by them if they're 0, right? So they have to, as long as they're greater than 0, then we can divide by them. And the other thing is we've got these additional constraints. So if q of x hat is greater than 0 for all x, then this basically defines this many, the size of the alphabet of x hat equations, which along with the distortion constraint can be used to solve what is absolutely what's necessary for getting the conditional distribution. Because remember, if we've got q of x hat, we can then use that first expression to get us the conditional distribution based on the distortion. And then this gives us essentially, n plus 1 or something, the size of the cardinality of the set of x plus 1 equations, so that we can actually solve for the things that we need. Because at this point, we've eliminated a lot of the things that we need to solve for. So it means that there's obviously a lot of redundancy in this problem, just by looking at the analysis and the KKT conditions. Now the other thing that says is that whenever this is true, then this is true. And why is that? Well, we already said, actually, we already talked about why that is. But why is that? It's because of the form of the expression. And I have another slide next time that says that mu is not going to be infinite. But what this is giving us then is that, how are we computing the rate distortion function? The one thing that we're fixing is lambda. Like we're not solving for lambda. That we can think of that as a fixed parameter. And so if we choose a particular value of lambda, that can be used to compute a particular value on the rate distortion function. So that becomes the value for lambda. But we're going to see actually an interesting relationship between lambda and that function. And it turns out that we're going to see, I'll have a theorem in a minute that says this, that lambda is going to be equal to the negative of the slope of that point. So the idea is that we start choosing the slope, and that's going to give us a pair, an RD pair. And so then we get this expression. So given a set of values, lambda and q of x hat, we get the distortion function here. We get the distortion value. Here's the expression for it. And you can think of it as distortion as a function of lambda and these q's, right? And we also get a rate value, again based on lambda, which is a function of lambda and these q's. And we're going to sort of negate lambda because, and we're going to express it in terms of s in certain cases, because s is going to be exactly the slope. Now remember, s is going to be always a negative value, right? Because we know the shape of this function. The slope is either going to be negative or eventually it's going to be 0. Whereas lambda is going to be a positive value. Lambda is the negative of the slope. And so that's sort of one way of carving out the function. We can sort of trace through these different possible slopes and get the actual shape by doing this, this procedure. And then what happens is that as the slope becomes closer and closer to 0, we're going to start getting these points where q of x hat is negative, and then we just turn them off. We know that at that point we just turn that off completely. We set it to 0, and then solve it again. Okay. Again, that follows from KKT. So here's sort of the formal statement of the theorem. So it says basically, for all slopes greater than negative infinity, and then for the optimal q of x hat, if q of x hat given x is equal to 0 for any one x, then it's true for all x. So notice they turn off, a code word turns off altogether, not just based on one particular x. And therefore that x hat can be, that code word can be completely deleted from the alphabet. So to show this, let's bring in the inequality pair back in. So let's bring this guy in and sort of show the form of the expression. So here's the Lagrangian with this additional guy. And when we take the derivative and everything, we're going to get essentially a form. We're going to get the form in this particular case with the constraint. And the constraint is only going to pop up in the case when y is equal to negative x hat. So let's zoom in a little bit on this more so we can see it. So we're going to have, let's do this case first. So when y hat is not equal to x, so y hat is basically our x hat. I'm using y just for simplicity here. So q of y hat given x is going to be equal to this form that we saw before, where it's going to be q of y hat over mu of x times e to the s times the distortion. And s, remember, is the negative of lambda. And s is a slope, so it's going to be a negative value. And so that means that if one turns off, then the other one turns off. And then on the other hand, there's this other case where this is true, and we're going to get a very similar expression. First of all, we see that all of this stuff here still lies up in the exponent, right? So there's no chance of this factor ever becoming 0 as long as everything's finite. And again, the 0-ness of this guy depends entirely on the numerator, q of y hat. So the other thing to note is that mu is equal to this thing. Mu is always going to be greater than 0, thanks to its definition. We know from the fact that it's just a normalization. So and this particular function here, so f is sort of meant to be either one of those two exponents of e, depending on whether y hat is equal to x or y hat's not equal to x. But it's whatever, it doesn't matter, it's just some f. And that's going to be never equal to 0. And the above inequality, moreover, is strict thanks to the normalization property. And the fact that q of y hat is never less than or equal to 0 when we add that constraint. And thus, u is going to be greater than 0. And also, U is going to be bounded from above thanks to the fact that the distortion is upper bounded by D max. So we also have this property again. So there's never a chance of mu being infinity. So in other words, if this is true, if Q of x hat given x is equal to 0, it can only be due to Q of x hat being equal to 0. So all code words turn off together. So that, in some sense, is really, really lucky. Right? That's really, really good news because it means that we're not going to get a matrix where it wouldn't be bad if, say, only one particular x. So let's say if you have a very, very big alphabet. And this is the optimal solution, right? So if you have a very big alphabet and there's one x that has a very, very low probability, but for some reason that one x wants to use this particular code word. Right? So that means that would be sort of, God, that would be a waste. Yeah. So let's talk a little bit more about this. If there are not any questions, are there questions based on the theorem or the proof? Okay, so let's offer a little bit more intuition then. So this is what the theorem said. Now the next theorem is something that I mentioned, which is that the meaning of s and negative lambda is equal to the slope. In fact, if we take the derivative of r with respect to d in this optimization problem, what we're going to get is s. That's the slope. Negative lambda. It's the negative Lagrange multiplier. So what we're doing when we're choosing lambda, we're not is we're choosing the slope. So here's a nice picture. I'm not going to prove this there, but it's just a bunch of algebra. So so we're choosing the slope of that of that green line, and then that gets us this particular point here. So what we could do is we could just start choosing a bunch of slopes. Like we might start with like a very, very large negative value, and then maybe quantize the slope, and we could maybe pick out a bunch of points, along this curve, and sampled it for various different points, and then sort of interpolate it and get sort of a nice shape. And just do this numerically for each different value of lambda. So that's one way to do it. And so to get the resulting probability distribution itself, we actually need to find this marginal distribution Q of x hat. And if we do get any negative values, then we need to just remove that code word. We know they all come or go together, so we remove the code word and we repeat the procedure again. We just remove the code word and then optimize it again. And we continue this process until they're all positive. And we know that, again, this happens only when the distortion is big. This is not going to happen when the distortion is small. But eventually it will happen. If it is the case that we only have one left, then we know that that slope is at a point where there's only one code word, which means that the rate is 0. Okay. And there's only one code word. Because remember, if there's only one code word, then the rate is going to be 0. We know that it's always that code word. Now, on the other hand, this isn't so great because the solution to these set of equations is kind of difficult. You have to do matrix inversion or some sort of LU decomposition or something, and maybe you've got massive alphabet sizes, and maybe it's even a continuous alphabet. And so maybe it's not necessarily such a great way to solve it. It's certainly not as great of a way of solving it as the way that we're about to discuss. There's a much better way of doing it, and this is sort of the notion of alternating minimization. So alternating minimization, sometimes it's called alternating projection, but it was developed, I think, primarily in the information theoretic community, and Emil Scissor was sort of its prime proponent. And it was around the time, let's see if I can come up with a reasonably interesting historical perspective of this procedure. So there were a number of papers that were coming out. There was, in the statistical literature, there were people who were trying to do maximum likelihood estimation of mixture models. And while it's not convex, they were people were interested in trying to do this. And so even in the 1960s, people were trying to do this. And if you look at there's this famous pattern recognition book that came out in 1968 by Duda and Hart. I don't mean the Duda, Hart, and Stork book. I'm talking about just the Duda and Hart book. And that came out in like 68, 69. And in that book, it was sort of millimeters away from defining the EM algorithm. Then in 1972, Dempster, Laird, and Rabin came out with this paper which now has 400 billion citations on the EM algorithm. That was the Dempster, Laird, and Rabin paper. And then around the same time, 71, 72, Blehout and Aramoto, because people in the information server community wanted to come up with computational ways of computing both the channel capacity and the rate distortion function. The theory of rate distortion had been developed already by the early 70s, and channel capacity had been developed by Shannon in the 40s. But there wasn't yet a good way of sort of numerically and computational. Computers were becoming more and more important in the 1960s. People were actually beginning to get access to computer time on punch cards, where you could bring your deck of cards to compute something to some computer. And so that was becoming more and more important. And so the Blehout-Aramoto algorithm came out, and the EM algorithm came out, and maximum likelihood estimation. And then Scissor sort of seemed to notice that actually this seemed to be an instance of something slightly more general, called alternating minimization. And then he sort of developed in the late 70s and early 80s and came out with this paper in 1983, I think. It might have been a few years earlier. There were earlier drafts circulating around. But that's the paper that I mentioned on the web, on alternating minimization. And since that time, and I think to some extent partially parallel with that development, there was in the just pure convex optimization literature, irrespective of any particular application, like maximum likelihood estimation of parameters of a statistical model or computing rate distortion for information theory, there were people who were trying to do alternating projection-based minimization of multi-objective convex functions. There's also coordinate descent style optimization procedures. But let's say develop this alternating minimization procedure now. So the idea, the general idea is the following. So we start with two convex sets, let's say A and B. And so A and B are two convex sets. And there's some underlying distance. And let's for right now assume that it's a true distance. So let's say like it's a Euclidean distance or some sort of, like maybe a 2 norm, D of AB. And what the goal is to sort of try to minimize simultaneously over both of them. And D of A comma B. Now we're not necessarily saying that D is jointly convex. We're just saying that the sets themselves are convex, and we're saying that this distance is Euclidean. Okay. And now let's consider the following procedure, which seems sensible. You can think of it as like a divide and conquer procedure on the one hand. On the other hand, you can think of just something that's sort of intuitively obvious. That we start off by choosing an A naught. Let's zoom in on the algorithm a little bit so you can see it better. Let's choose an A naught arbitrarily. So we just choose any point inside of A. And then we iterate some number of times. We say, okay, well, let's fix fixing A naught, fixing the previous value of A. We optimize over B, and then choose the next point in B based on that optimization. And if there's ties, we break ties arbitrarily. And now we fix B, and then we optimize over A, and then choose A this way. So we've now, starting from one point, we've chosen 2 points. And then we just iterate. We go back and forth, optimizing one, holding the other fixed, and optimizing the other, holding one fixed. And we alternating minimization. Right? So that's a nice idea, right? Especially if certain properties are true of this. Now, what would be nice would be if it's the case that this procedure really does get us to the true minimum. Are we guaranteed? No. Can we understand when this might be true? This is what Scissor did. Number 2, what if it's the case that doing this minimization is analytically very, very difficult? Like maybe there's no closed form solution, no closed form analytic expression for this simultaneous minimization. But what if there's a closed form analytical expression for each one of these minimizations? Meaning that we can just set the value to its expression. That would be really great, because it would mean that each step, lines 3 and lines 4 of this algorithm, would be very, very easy to work. We just set its value. So we do one step, and then another step, and then another step, and we just keep doing this. There's no iteration, there's no process, there's no multiple, there's no lack of solution. So let's now notationally switch to scissors notation. Now, rather than A and B, let's use script P and script Q. Okay, but does everybody get the idea of what's happening? Okay, good. So, here's where we jump to the animation. So this is the alternating minimization graphic. And I'm not touching the iPad now, I'm touching PowerPoint. So this is thanks to PowerPoint. So basically we've got these two convex sets. We've got this one, and we have some distortion or distance d of PQ. And we have, we might choose a P in script P and Q in script Q. And so we start off by choosing some Q naught inside of Q, which is down here, right? And then we find P1 to be the point in P that's closest to Q. So first of all, it makes sense that it's going to be on the boundary of this convex region right here. And then secondly, it makes sense that it's going to be on a point and there's a tangent line. So this line is going to be orthogonal to this line. Okay, so then we do the opposite. We next find the point inside of Q that's closest to this P1. And let's call this guy Q1. So here's the result of this minimization. Right, so P1 is fixed and we're optimizing over Q to give us Q1. And again, it's on the boundary of Q, and there's an orthogonal at that point that it's at, which is orthogonal to the vector between P1 and Q1. And then we keep doing this. We get P2 inside of P and Q2. And you can see that at each step, thanks to the convexity of each of the regions, the distances are getting smaller and smaller. Remember, the goal is to sort of get the 2 points that are closest to each other in these 2 convex regions. And by alternating back and forth, it seems reasonable to assume that under certain circumstances, this procedure will get us the optimum. Even if it's the case that we're not necessarily using the Euclidean measure, which is what obviously this is doing here. Because our sense, our visual capabilities as humans, as fellow humans, we can all visualize quite nicely in 2 or 3 dimensions in Euclidean space. But as soon as we go to n dimensions in non-Euclidean space, for example, something that might be measured by like a Kullback-Leibler divergence, our intuitive sense isn't as useful. But on the other hand, maybe we can still prove that alternating minimization in certain circumstances will give us the true global minimum. And that's in fact what we're going to do. So I think that's the end of this. Okay, so actually that's not what we need. So let's go back to this. So how did you like the animation? Technical success. A little bit of a stumble, but relative.
That's converted to PDF.
Oh, converted to PDF. Yes, you're absolutely right. That wasn't animated enough to warrant being in PowerPoint, was it? You're absolutely right. Next time I will do that. So. Okay, so in the next lecture, actually possibly even in this lecture, in the next 7 minutes of class, no, actually probably in the next lecture, what we're going to do is we're going to prove under the conditions under which this guy, the limit, as n goes to infinity of this sequence of pairs, a n, b n, converges to, or I should say, d of a n, b n converges to d of a star, b star, where a star, b star is the true minimum, and where this limit is equal to a star and this limit is equal to b star. And as you will see, where these ANs and BNs are obtained via the alternating minimization process. What I'm hoping we can do maybe a little bit today is map the rate distortion and also the channel capacity finding problem into this paradigm. So first of all, and this is a really important result, even outside of computing rate distortion or channel capacity, and even outside of alternating minimization. This is an important result, first of all, because it's very, very applicable to many, many problems. So let's sort of set up the problem, and I really want everybody to understand this. So we've got this joint distribution P of x, y, which can be factored anyway, right? We can say it's equal to P of x times P of y given x, or P of y given P of y times P of x given y. Let's factor it in this particular way, P of x times P of y given x, right? Now, let's define R star to be this marginalization. So R star y is just basically taking this joint and then marginalizing out x to get the marginal on y. But we're just calling it R star for some reason. We could call it P of y, R star of y. We could call it P of y. Let's call it R star of y for the sake of this theorem. And what the theorem says, let's zoom in a little bit on it, is that we perform the following optimization of the Kullback-Leibler divergence, where this guy is just P of xy, right? This guy here, this is still the same P of x, right? This is just the same. And this is just any R of y. The point is that this has to be a product of marginals, right? So the product of marginals, and it's saying when we minimize over R, over this probability simplex, so we want to find, and another way of thinking about it is that P of x is fixed. We've got this joint distribution here, and we want to find the P of y such that if we were to take two random variables, x and y, that were independent, find me the distribution over those two independent random variables that's as close as possible to the joint. Although the one distribution on P of x, that's fixed, right? So I've got P of x, the distribution over P of random variable x is fixed. I'm now trying to find the marginal over y that renders the independent random variables x and y as close as possible in terms of its joint distribution, which necessarily is factorized in this form here. Make that as close as possible to the joint. And what distribution does that? Well, it's R star, the marginal. So the marginal is the best way, when you want independent random variables to be as close to the joint, compute the marginal. So from this sense, the closest independent, this may seem obvious, but it's a formal result to say that the closest independent random variables to the joint distribution are by computing the marginals in the Kullback-Leibler divergence sense. Okay, everybody understand the statement of the theorem? So the next theorem is a very similar theorem. It says, and very similarly important as well, it says we've got this numerator, which is just P of xy, which we've decided to factor in this particular way, P of x times P of y given x. And then here we're just normalizing it, right, which is just the sum over x, P of xy, which just gives us P of y. And that's definitely going to be P of x given y, right? But let's just call it R star, because R star is going to be our optimal solution to an optimization problem. So the optimization problem in this particular case is going to be again a very similar optimization problem, but in terms of mutual information rather than Kullback-Leibler divergence. So here's like the mutual information, and what we want is we're fixing P of x, and we're saying amongst all probability distributions R of x given y. So this is the thing that we're optimizing. All of this stuff is fixed. What's the one that maximizes this quantity, that maximizes this, what is like a mutual information quantity? It's kind of like, you think of it as in some sense like a relative mutual information quantity. Right? Because in this optimization, it's not necessarily the case that P of y given x is equal to P of y given x is equal to this. In fact, they're not even the same order of variables. We can always factor this as P of y given x, P of x given y times P of Right? It doesn't matter. That could be written that way. So it's not necessarily the case that that R of x given y is going to equal to P of x given y inside of the optimization. But the point of what I'm trying to say is that the result of this maximization is this sort of conditional marginal, is this guy here. There he is, achieving optimality. Look at him go. Isn't he great? I'm very proud of R star. He can do all sorts of things, or maybe he's a she. She can do all sorts of things, including win the contest of maximizing over the two-dimensional probability simplex of that quantity. So I think we should stop at this point because the bell has reminded us that this is the end of class. But what we're going to do with these results is, and remember before we go, let me just say this one last thing. So remember before that I said that marginalization is a form of projection? Well, here's marginalization and here's projection. Here's a D, and we're projecting it. We're finding the closest R using the KL divergence. And similarly, here's another projection, and here's another form of conditional marginalization. That's just the conditional distribution. So we're starting to assemble these pieces of the puzzle. We've got marginalization as projection, we've got these minimizations, and we've mentioned alternating minimization. And with these pieces of the puzzle, what we're going to do next time is glue them up together and see how rate distortion and channel capacity can be solved using alternating minimization. Very, very simply. Especially when you see how unbelievably easy, like for example, these marginalization steps are unbelievably easy to compute. It's just summing over a table. And whereas if you saw equation 25.33, you might get very frightened and discouraged. But when you see this, you get happy and enlightened and willing to code up a Perl script. Okay, anyway, I will see you guys on Monday. Start thinking about papers that you want to review.